Remember when I told you no matter where I go, I'll never leave your side, you will never be alone. Even when we go through changes.
Now we're down to our sixth topic, sedimentation. Overview. Sedimentation concept, determination of Vs and determination of Vo are the subtopic under sedimentation. Start with overview. Particles that will settle within a reasonable time, a period of time, can be removed in the sedimentation basin, also called as clarifier. There are actually four zones. First one is the intel, second is the settling, third is the sludge storage, and the fourth one is the outlet. So now here we have the different schematic on the zone of sedimentation. First photo is horizontal flow clarifier and the second one is a vertical flow clarifier. Although there are different kinds of clarifier, they still have those four zones I've mentioned a while ago, which are the inlet, settling, outlet, and the sludge storage zones. Now let's go deep into the different zones. First, we have the inlet zone. So the purpose of inlet zone is to evenly distribute the flow in suspended particles across a cross-section of the settling zone. The inlet zone consists of series of inlet pipes and baffles placed about 1 meter into the tank and extended the full depth of the tank. At some point, the flow pattern is evenly distributed and the water velocity is slowed to the designed velocity of the sedimentation zone. At that point, the inlet zone ends and the settling zone begins. This is the inlet zone. With a well-designed inlet baffle system, the inlet zone extends approximately 1.5 meters down the length of the tank. Proper inlet zone design may be the most important aspect of the removal efficiency. With the improper design, the inlet velocities may never subside to the settling zone design velocity. Typical design numbers are usually conservative enough that an inlet zone length does not have to add to the length of calculated for the settling zone. In an accurate design, the inlet and the settling zone are each designed separately and their lengths are added together. For our sludge zone, the configuration and depth of the sludge storage zone depends upon the method of the cleaning, the frequency of cleaning, and the quantity of the sludge estimated to be produced. All these variables can be evaluated in the sludge storage zone design. And for our outlet zone, is designed so as to remove the settled water from the basin without carrying away any of the flux particles. A fundamental property is that the velocity of the flowing water is proportional to the flow rate divided by the area through which the water flows, and that is V is equal to Q over A subscript C, which is water velocity is equal to the water flow over the cross-sectional area. The town of Urbana has a low turbidity raw water and is designing its overflow weir at the loading rate of 150 meter cube per diameter times meter. If its plant's flow rate is 0.5 meter cube per second, how many linear meters of weir are required? All that we need to do is to get all the values given in the problem. Just need to divide 0.5, which is our flow rate, to our loading rate of 150, and that 86,400, and that's a conversion factor, so that we will end up with a meter, a unit of meter. Just need to calculate it and we will get an answer of 288 meters. It's time to go to the sedimentation concept. There are two very important terms to understand in sedimentation zone design. The first one is the Vs, or the settling velocity, which is the rate at which particle is settling downwards. And the second one is the Vo, or the overflow rate, a velocity at which a tank is designed to operate. It is the velocity of liquid rising and sometimes referred to as the surface loading rate. When the settling velocity is greater than our overflow rate, expect 100% particle removal. But if ever our settling velocity is less than our overflow rate, expect 0% removal. The easiest way to understand these two concepts is to view an upward flow sedimentation tank that is shown in this figure. In this design, the particles flow downward and the water rises vertically. The rate at which a particle is settling downward is a particle settling velocity. This one, that arrow that points downward, that's our particle settling velocity. And the velocity of the liquid rising is the overflow rate. That arrow pointing upward is the overflow rate. Obviously, the particle is to be removed from the bottom of the clarifier and not go out of the settling water or the settled water. Then the particle settling velocity must be greater than the liquid rise velocity, or what we call the overflow rate, as what I've mentioned a while ago. In design, the procedure would be to determine the particle settling velocity and set the overflow rate at some lower value. Often, V sub O is set at 50 to 70% of our V sub S for the upflow clarifier. Overflow rate is the same as the liquid velocity. Our overflow rate is equal to the volume over time all over surface area, which is also equal to depth times surface over time times surface, and also equal to depth over time is equal to the liquid velocity. VO is also equal to the volume of the tank divided by the detention time over A sub S, which is also equal to H times A sub S over detention time times A sub S, which is also equal to H over TO, or our detention time. While our VS is equal to H over TO, our detention. Since Vs is equal to H over TO, and since TO, as you can recall, it is equal to the volume of the tank over the volumetric flow rate, so we can say that our Vs is equal to H over the volume of the tank divided by our volumetric flow rate, which is also equal to H times the volumetric flow rate over the volume of the tank. But we know that the tank volume is described by the product of the height, length, and width, so we can rewrite this as Vs is equal to H times our volumetric flow rate over length times width times height, which is also equal to volumetric flow rate over length times width, since makancel man ang height dira at taas. Okay? And the product of L times W is the surface area. Simply saying that Vs is equal to volumetric flow rate over our surface area. For the percentage of particle removal, which is P, is equal to 100 times the quotient of Vs and Vo, or settling velocity over the overflow rate. Since we already talked about percentage particle removal, now we'll have problem related to that. The town of San Jose has an existing horizontal flow sedimentation tank with an overflow rate of 17 meter cubed per diameter times meter squared, and it wishes to remove particles that have settling velocity of, so like 3 different Vs or settling velocities. First one is 0.1, second is 0.2, and third is 1 millimeter per second. So same silang units din. The question now is, what percentage of removal should be expected for each particle in an ideal sedimentation tank? So the first thing we need to do for our first 0.1, first settling velocity, first we need to convert our overflow rate so that it will be compatible to the unit of our settling velocity. Since the compatible unit is millimeter per second, we need to have conversion factor that will lead us into a millimeter per second unit. So after that, this is a conversion factor, this one, and then after calculating that, 17 times 1000 divided by 86,400, and crashing out all the units that must be crushed out, it will lead us to 0.2 millimeter per second, which is the ideal or compatible unit. Now, the next thing we need to do is just to plug in
the given or what we have to our equation. We already have the equation for percentage particle removal, which is P is equal to 100 times the quotient of the Vs and the Vo, or 100 times Vs divided by Vo. So since we have the Vs, and that is 0.1, we just put it in the upper part, and our Vo, as you can see after converting, it's 0.2. Just put it in the lower part and then just solve, calculate, and that will lead us to 50, which means that we have 50% removal, or there will be 50% particles that will be removed after that. So that's our answer for the first one, for the first settling velocity, which is 0.1. For the next one, we have 0.2. This particle have Vs, or settling velocity, is equal to the overflow rate, and ideally will be 100% removed. So, kanina 50, kanina 100. Now, for the third one, we have here 1. Our settling velocity is 1. This particle have Vs is greater than Vo, and 100% of the particles should be easily removed. So, recall lang ta, ang first natong answer sa atong 0.1, it's 50% removal. For atong B, which is 0.2, 100% removed, or removal, diba? Ang third nato, or ang C, is 1, which is also 100% of particles should be easily removed. So, muna ato ang sedimentation concept, muna problem sa percentage particle removal.
Determination of Vs particle settling velocity. In the design of an ideal sedimentation tank, one first determines the settling velocity, or the Vs, of the particle to be removed, and then sets the overflow rate, or the Vo, at some value less than equal to the Vs. Determination of the particle settling velocity is different for the different types of particles. Settling properties of particles are often categorized into one of three classes. Determination of Vs. So now we're down to different classes. Type 1 sedimentation is characterized by particles that settle discretely at a constant settling velocity. They settle as individual particles and do not flocculate or stick with other particles during settling. Example of this particle are sand and grit material. Generally speaking, the only application of type 1 settling is during pre-sedimentation for sand removal prior to the coagulation in a potable water plant. In settling of sand particles during cleaning and rapid sand filters, and in grit chambers. Now, for the second sedimentation, or type 2 sedimentation, it is characterized by particles that flocculate during sedimentation. Because they flocculate, their size is constantly changing. Therefore, the settling velocity is changing as well. Generally, the settling velocity is increasing. This type of particles occur in alum and iron coagulation, in primary sedimentation, and in settling tanks in trickling filtration. For our type 3, or zone sedimentation, particles are at high concentration, greater than 1000 milligrams per liter, such that the particles tend to settle as a mass, and a distinct clear zone and sludge zone are present. Zone settling occurs in lime softening sedimentation, activated sludge sedimentation, and sludge thickeners. For the determination of our overflow rate, or Vo, the settling velocity corresponding to a given turbidity at time t is given by Vs is equal to 10 centimeter over t time in minutes. It sounds confusing that I'm talking about Vs, when in fact we're here to determine the Vo. But later on with our problem, you will understand how this Vs will help us to find Vo, or our overflow rate. For the last problem, a jar test was performed using alum as a coagulant, and turbidity samples were taken between 2 and 20 minutes of settling. If a settled turbidity of 1 NTU is desired, what is the effective flux settling velocity and the corresponding design overflow rate? Solution. At 1 NTU, the settling time was about 3.6 minutes. Therefore, the effective particle settling velocity was, since in our previous formula or equation, it should be 10 cm over the time.
since we already have our time and and 10 is constant, so we just need to divide 10 with 3.6 in order for us to get our Vs, or our settling velocity, and that will give us 2.8 cm per minute. If the overflow rate was set equal to the settling velocity, the overflow rate would be, so here, this is what I'm talking about. There are some problems that we need to set our overflow rate to be equal to our settling velocity. That's why Vs will help us to find the VO. To find VO, we just need to use some conversion factor in order for us to arrive into the required unit for our VO. So it's actually a long process, but it's all just for changing the unit to make it a VO. So at the end, we'll get the VO, or the overflow rate, of 0.629 GPM per feet squared. That's for a sedimentation problem.